Hello, calculus students and seekers of truth. We continue our study of improper integrals, this time with a different case. This is the case of the function secant squared of x integrated between 0 and pi. And these scenarios are trickier than the first types because if you look at this, it doesn't tell you. The integral doesn't reveal itself as being improper. Looking at the previous examples, the last videos, you see there when there's an infinite symbol. Okay, so when you have a symbol that says infinity, right, these two integrals are basically shouting at you that they are improper. This one is also improper, but it's a little bit sneakier. And so to really understand why these integrals are improper, we have to understand this function, secant squared of x. You really have to know and understand the secant function. So the secant function, right, is really 1 over cosine of x, and this is undefined for x equals pi over 2. It's undefined at a bunch of other places, but at least on the interval 0 to pi, this graph is, or this function is going to be undefined. So, and not only that, this is going to be a non-removable discontinuity. Okay, so this is where things get really tricky. It's very tempting to just use the antiderivative. You got tangent of pi, tangent of 0, and solve it that way, but that would be incorrect. There is a undefined point in here, so we have to reconcile that. So the way we deal with this, actually let me start by drawing a picture of this graph so that we can understand it and see it a little bit more visually. All right, so there's a picture of the function secant squared, and you see here that at this point here, pi over 2, you have a discontinuity, a non-removable discontinuity. It's a vertical asymptote, and we want to know this area right here, right? And we're not quite sure if this area is going to be infinite or not. Remember, looks are very, very deceiving when we're dealing with these improper integrals. Okay, so this region right here, well, maybe it's finite, maybe it's infinite, I don't know. But we have to break this integral up into two smaller integrals. So first, the one that's on the left side here. So that would be the limit as, let's make another variable, let's call this b. As b approaches pi over 2 from the negative side of the integral from 0 to b of secant squared x dx. And then there's the integral on the right side here. So we're going to add that. That is the limit as some other constant in abstraction, a, approaches pi over 2 from the positive side. So it's like we're getting closer to this vertical line from the positive direction of the integral from a to pi of secant squared x dx. Okay. So the antiderivative of secant squared is tangent, and that's true for both of these parts. And we're taking the limit as b approaches pi over 2 on the negative side. And this is evaluated between 0 and b. And over here, same limit as a approaches pi over 2 from the positive side of tangent of x that evaluated between a and pi. Okay. So now we can go ahead and make our substitution. So this is tangent of b minus tangent of 0 plus tangent of, let me leave some room here for the limit, tangent plus tangent of pi minus tangent of a, okay, with the limit here as x, or as a approaches pi over 2 from the positive side, and over here it's the limit as b approaches pi over 2 from the negative side of this entire expression. Well, some nice things, right? So nice things here are that the tangent of pi is equal to 0 and the tangent of 0 is equal to 0. So now all we have to do is understand what's the limit of the tangent function as b approaches pi over 2. Now go watch some of the older videos on the tangent function, or graph the tangent function, or reevaluate the unit circle for the tangent function to understand this point. But we know that as b approaches pi over 2, the tangent function is going to approach infinity. Okay? And then on the other side of it, as a approaches pi over 2 from the positive side, it's going to approach negative infinity. And I'm doing something that's a little bit sloppy here. I'm using infinity as a number, and again, it's really not. It's just a way to intuitively describe what's going on. So what we have here is a large number minus the negative version of that large number. So in the end, we're going to get 2 times the very large number. We're going to get, in other words, 2 times infinity. So that's going to be just a very, very large number as well. So we can say in this case that this function, this definite integral, this improper integral, is divergent. All right, so I highly recommend you pausing the video at this point, working this out by yourself, and then hitting play again. Did you do it yet? All right, let's see. Let's see how you did here. So same thing here. This has a discontinuity, right? So this is discontinuous, and not only that, it is a non-removable discontinuity at x equals 0. Okay, so what we need to do is rewrite this a little bit differently. This is going to be the limit as some constant in abstraction, a, approaches 0 from the positive side. The integral from a to 1. And I'm going to rewrite this expression here, instead of over the square root of x, I'm going to write it as x to the negative 1/2 dx. Okay. So working out the antiderivative, this is going to be 2x to the 1/2 evaluated between a and 1, was using the limit as a approaches 0 from the positive side. Okay, so this is the limit as a approaches 0 from the positive side of 2 times 1 to the 1/2 minus 2 times a to the 1/2. Okay, so this first part right here, 2 times 1 to the 1/2, that's just equal to 2. And the limit as a approaches 0, in other words, as you put in a very, very small number in for a, 0 to the half power, or the square root of 0, is also equal to 0. So that just turns out to be 2 times 0. So this is gone. So our final answer is just equal to 2. And again, this illustrates kind of like, if you look at the graph of this function that we're integrating over and the previous function, it is once again very unintuitive. There is really no reason clearly why. So here's the function 1 over root x. There's really no reason why this area right here would have to converge, or would have to eventually be equal to 2. Whereas the area that we saw in the previous problem is going to grow forever without bounds. Okay? So again, we get a better sense of this later on when we work with infinite series. For now, we work out all of the fundamental theorem of calculus and all of the algebra using limits in order to deduce our answer. As always, keep working hard. Ask for questions when you need it. Thank you for watching, and have a wonderful day.